We will now talk about the notion of propositional equivalences. Okay, so we mentioned the notion that we can build compound propositions, and we can build as many compound propositions as we want. In fact, you can build an infinite number of them. But the question is that if someone gives you two compound propositions, are they equivalent or not? What does it mean to be equivalent? Just as we have the notion of equality between two numbers, the notion of equality between two sets, between two strings, and so on, we have a similar notion for propositions. So we say that two propositions are equivalent basically if they are either both are true at the same time or false at the same time. Okay, in other words, if P, if and only if Q is a tautology that's always true, then these two are equivalent. Okay, so the simplest way to determine if two propositions are equivalent is to build the truth table and then look at the two columns that correspond to these propositions. If they are equivalent, then what you should see in these two columns is that either both of them are true or both of them are false in any row. Okay, so you look at every row, they have to be either both true or both false. Okay, so for example, two of the most famous and most useful equivalences are what we call De Morgan's laws. Okay, so what is the first one saying? The first one here is saying is that the negation of a conjunction is the disjunction of negations. So the negation of P and Q is the same as not P or not Q. Okay, and the second one says the negation of disjunction is the same as the conjunction of negations. As I said, if we want to show that these two are equivalent, or the first one, if I want to look at the first one, so then I can build the truth table of, negation of P and Q, and I can build the truth table for not P or not Q, and I can look at all possible combinations here. Again, what I should see on these two columns now that are blank is that in every row are either both true or both false. Okay, so let's look at them here. So when P and Q are true, then P and Q is true, but the negation is false. And when P and Q both are true, then not P is false, not Q is false, then false or false is false. When P and Q are, one is true and one is false, then P and Q is false and the negation is true. And the same thing on the right here, one of them is true, the other is false, therefore it is true. And this one here is true, this is true. If both of them are false, then this is true, and the one on the right hand side is true. So if you look at this table that we just built, both of them are false here, both of them are true, both of them are true, both of them are true. In other words, we just showed that not P and Q, if and only if not P or not Q is a tautology. Okay, so this is why these two statements or these two propositions are logically equivalent. In other words, if you write one, it's the same as writing the other. Or if you want to prove one, it's the same as proving the other. Okay. Another very important implication is this one here. P implies Q is equivalent to not P or Q. So if you build again the truth table here for P, Q, and P implies Q and not P or Q, you will notice that they will have the same values in the right two columns here. So we said this is true, this is false, this is true, and this is true. The same thing if you look at the right hand side here, if you try to evaluate this is going to be true because Q is true. This is false now, the second one, because Q is false and negation of P is false. So false or false is false, and this is true, and this is true. Now look at this here. Both of them are true in this case. Both of them are false. Both of them are true. Both of them are true. So these two here, this one and this one, are logically equivalent. So if someone asks you to prove P implies Q, a different way to look at it is to prove that either P is false or Q is true. This is the same thing. So if you prove that either P is false or Q is true, in some sense you have proved that P implies Q. Now, there are many other equivalences. We are not going to go and build truth table for each of them. It's a tedious and boring step, honestly. But if you look, for example, at this, they should make sense. The negation of P is P, right? So double negation, cancel the negations cancel out each other. Commutative laws. So P or Q or P are the same, right? So if you swap the order of two propositions around the disjunction or around the conjunctions, it's the same. Distributive law is basically you can distribute across a disjunction or across a conjunction. Okay. Implication laws, again, as I said, are very important. I want to highlight, actually, of these ones here, I want to highlight this one here. This is very important. We use it a lot in proofs. We will get to it at some point. That if someone says prove if P then Q, but you instead prove if not Q then not P, you have done exactly the same. Okay, so if someone asks me to prove if the statement if P then Q, and I decide to prove if not Q then not P, I have proved exactly what they asked me to do, because these two statements are equivalent. And the one on the right here, P if and only if Q, is the conjunction of P implies Q and Q implies P. This is why when we want to prove a theorem of the form P if and only if Q, the proof usually has two parts. One is, let's prove first that P implies Q, and the second part, let's prove that Q implies P. Okay, where does that come from? It comes from this logical equivalence here. Okay, as I said, using truth table is the standard, the simple way for establishing whether two propositions are equivalent, but sometimes that's tedious. And again, as we said, this can be also very time consuming. So another way to establish equivalence is by actually using a sequence of equivalences of ones that we have already established to get at what we want. So for example, suppose I want to prove that not P implies Q is equivalent to P and not Q. One way to do that is as follows. So I can say not P imply Q. I know that this is equivalent to not P or Q. Where did I get this from? I've established on the previous slide or two slides ago that P implies Q is the same as not P or Q. So I can replace P implies Q by not P or Q. I can say now, using De Morgan's law, that this is the negation of P and not the negation of Q. Right? So if the negation of the disjunction is the conjunction of negations. And now I can say that this is equivalent to P and not Q. Where did I get this? Because negation of P is equivalent to P. Okay? And basically I'm done, right? Because this is what we wanted to show, that negation of P imply Q is the same as P and not Q. So this way is simpler and more elegant, honestly, than building a truth table. But this is where you start seeing what's so hard about establishing a proof. While the truth table is such a mechanistic way, such a standard or normal way of doing things by just building exhaustively every possible row, this one here is no longer the same. Because this one now, if you look at it, why did I decide, from going from this one to this one, why did I decide to use that equivalence? As I said, we can build an infinite number of equivalences. Which one do I use? This is why establishing proofs in this sense is a hard exercise. And proofs are really, how do you establish a proof, is really an art more than a procedure that we follow, because the number of possible paths that we can take to establish a proof could be infinite, and so many of them lead us to dead end that doesn't take us to what we want. And getting to the right path and getting to it quickly in a finite amount of time, right? We don't want to take 15 years to establish a proof in general. This is why it is hard usually to establish proofs, and the way to do it is to practice more and more by doing exercises like this, so that you get the gist of it and you start understanding how do we rule out certain paths and how do we pursue some paths and so on. As another example, suppose I want to show the equivalence of these two statements and I don't want to use the truth table. So I can start again with the left-hand side. And you don't have to start with the left-hand side. Sometimes you can start with the right-hand side as well. Okay, so I want to show the negation of P or not P and Q equivalent to that thing on the right. So I can now use De Morgan's law, and I say this is equivalent to not P and the negation of not P and Q, right? So this is De Morgan's law. Now I can say that this is not P, and I can now apply De Morgan's law again, and this becomes the negation of P or negation of Q. This is equivalent to the negation of P, and negation of P is P or negation of Q. Then now I can use the distributive law, right? I can distribute across this conjunction, and I say this is the negation of P and P, or the negation of P or the negation of Q. Okay. Sorry, this is the, I apologize. This is the end here, right? So now think about this, the negation of P and P. This is a contradiction. This is false. Or the negation of P and negation of Q. False or anything, when is this true? The false doesn't mean anything. For this to be true, the right-hand side has to be true. This is equivalent. This is simplification. I can get rid of the false and the disjunction here. This is equivalent to not P and not Q. And this is exactly what we wanted to show, that these two, this one and this one here, are equivalent. So this is, this is the way to use logical equivalences to prove other equivalences without building the truth table here, okay?